Okay, so welcome everyone to the final session of day. So let's get started. The first talk is by Arushi Bodas, and she is going to be talking about seeing highly anisotropic gravitational wave backgrounds from the early universe. You can get started.
Thank you so much. Thanks to the organizers for inviting me and giving me the opportunity to talk about my work. Today, I will mostly focus, I'll be telling you mostly about how we can possibly see very, very anisotropic gravitational wave backgrounds from the early universe. It's based on this work that I did in my PhD with my advisor and some ongoing work if I have time. Can you hear me in the back? Thank you. Okay, so the inhomogeneous distribution of energy density in our universe, as seen in, for example, the temperature anisotropies of the CMB, the galaxy distribution is a very important cosmological observable. And the simplest explanation for its origin is the quantum fluctuations of a scalar field stretched to macroscopic length scales by inflation. And because of this connection between inhomogeneities and inflation and the super horizon freezing of these perturbations, such anisotropy maps are very important and unique windows into the inflationary physics, which is as far back as we can go. Now, current observations suggest that the density perturbations in all species, in standard model, even in dark matter, come from the same inflationary fluctuation, or in other words, they're adiabatic in nature, which means that if the future data sets that we hope to see, such as line intensity maps or just more data from large scale structure, we already kind of know what to expect in a sense or know what not to expect. So the CMB observations already put some constraints on the prospect of new physics that we can see in these new kind of cosmological data sets that we may have in the future. So maybe we can think in a completely tangential orthogonal direction. Can we think of an anisotropy map that is just very, very different from CMB, just completely uncorrelated, completely different from CMB? And so if you start thinking on this direction, the first question would be, okay, what would this map look like? What is the messenger? Just like CMB's messenger is photons, what should we think about? If you start thinking along these lines, you would realize that there must be some criteria that this map should follow. So first of all, whatever it is that is bringing us this different information, first of all, should be copiously produced in the early universe. Otherwise, we have nothing to see. Second, and kind of maybe the most important criteria is should be free streaming after its production for most of the time, because if it thermalizes with the standard model, then you would just have you will see something that's just a superposition of these two information. So you will not have any independent, you will not be able to see an uncorrelated map. We should have some technology to detect them today, right? Or potentially in the near future. And it is kind of, it's just a small list, but it turns out to be quite hard to satisfy all these criteria. But one thing does satisfy these criteria, and which is the topic of this workshop, gravitational waves, right? So of course there are various sources of gravitational waves in the early universe. But I want to focus on one in the beginning just to give some concrete example of what I'm talking about. So let's consider gravitational waves produced from some first order phase transition. And we have seen in much detail what this looks like, but maybe quickly, whenever the temperature of the plasma goes below some critical temperature, the system transitions from one phase to another through nucleation of bubbles of true vacuum. And the collisions of these bubbles is a very violent event. It gives rise to a lot of gravitational waves. Also, a nice things about first order phase transition is because there's some reason theoretically to believe that there might be phase transitions in kind of multi-TeV range, which in terms of frequency falls within these future space-based experiments like LISA and BBO. So a good kind of target to have. Okay, so just to see, like, if I have a phase transition, how do I think about the anisotropies of this phase transition? Let's kind of quickly recap to the CMB anisotropies that we all kind of know. So a quick recap, so here on the left, we are kind of in the center. I'm drawing in purple the surface of constant temperature at last scattering. Now, of course, if the universe was completely homogeneous, it would be a perfect sphere around us, but it's not. Because of the inhomogeneities, this surface is distorted. And because of these distortions, the photons, which are released at the same temperature, they travel different distance towards us, and there is kind of a differential redshift. And hence we see temperature anisotropies in the CMB, and we know that they're at the level of 10 to the minus 5. Now we can do the same thing with phase transition. Now here in pink, I've drawn the surface of constant critical temperature at phase transition. And for the exact same reason that our universe is not homogeneous, this surface will be distorted. And the gravitational waves, when the phase transition happens, the gravitational waves that we receive in different directions will have different redshift. And so you would expect different energy density coming from different directions in the sky and the anisotropy in gravitational wave background. Now, of course, if the phase transition is happening in the same kind of plasma that is eventually giving a CMB, then you would expect, at least on large scales, that these anisotropies are completely correlated. And the anisotropy in the gravitational wave background, which is the fractional anisotropy, should also be at the level of 10 to the minus 5. But what if the phase transition is not happening in the same plasma as the CMB? What if it's happening in some secluded dark sector that has a completely different origin from inflation? In which case, the surface of this constant critical temperature will not, it will look very different from the CMB, and the anisotropies you would expect would be uncorrelated and different. In particular, they will not be at the level of 10 to the minus 5. They can be much larger, and actually, I will show that that is the most interesting case. And another interesting point would be, so in CMB, there are all these things that you try to see. You try to see features in the power spectrum. You try to see non-gaussianities. We haven't seen anything in the CMB, but this map could be just full of them. You could do everything you try to do with the CMB with this new map that you get in gravitational waves. So of course, a different origin means we are thinking about some kind of multi-field inflation, right? So to get a different quantum fluctuation, you need additional field during inflation. So we will be thinking about inflaton, which is canonically driving inflation, and some kind of axion-like particle, which is a spectator, an auxiliary field during inflation. So during inflation, we have just the inflationary potential, which is slow rolling. At the end, the inflaton will fall into the valley. While oscillating, it will reheat the standard model dark matter, the usual things. And so the fluctuations, quantum fluctuations of the inflaton, you would expect should get directly encoded in the fluctuations of this standard model plasma. This is the usual story. That's at the level of 10 to the minus 5. This is the usual expression. Now, in addition, we would like to add another field. Let's call it chi. This field is initially misaligned and kind of stuck at some large value due to Hubble friction. And it has its own quantum fluctuations. At some later time, when the Hubble is equal to the mass of this chi field, the field will start rolling. And similar to the inflaton, at the bottom, it will reheat some sector. It's a different secluded sector, which is the source of our new map, gravitational wave map. And of course, the fluctuations of this chi field should be translated to the fluctuations of this secluded sector after reheating. So this kind of setup was used by the group at University of Maryland to kind of propose this idea of isocurvature gravitational wave background. And the idea can be kind of shown schematically in this kind of energy density versus time diagram in this post-inflationary cosmology. So as I said, during inflation, there are two fields, inflaton and the alp field. So after inflation ends, the inflaton kind of dumps its energy into some kind of precursor to standard model or standard model in dark matter, which just dilutes like radiation. let's just call it, so this sector does not undergo any phase transition, does not take part in phase transition, so let's call it non-PT sector. And on the, it just keeps diluting like radiation, it has the usual story. On the other hand, the ALP, after inflation, it dumps its energy into some sector that will undergo first order phase transition, which will give rise to the gravitational waves, and it will keep diluting like radiation. And to avoid some isocurvature constraints, you can just take this sector at some late time to just decay into standard model particles and kind of merge with the other sector. And then at late time, you have CMB being released. So what is one of the important parameters is how subdominant is this chi sector to the non-PT sector coming from the inflaton, and its character as this fraction of energy density in the subdominant sector is I'll just call it FPT. Now we can quickly write down what are the fluctuations in the gravitational wave and CMB. So of course, the fluctuations of the gravitational wave should have contributions from the fluctuations, primordial fluctuations of chi. And on top of that, because of the Sachs-Wolf effect, it will also have fluctuations from the dominant fluid, which is basically this non-PT fluid coming from phi. All good. And in CMB, you would expect the fluctuations from phi, of course, and then some subdominant contribution from this sector because it's merging at the end, right? Now, of course, if the fluctuations in the chi are much larger than the fluctuations of the phi, much bigger than 10 to the minus 5, then the gravitational wave anisotropy will be mostly dominated by the chi sector, while and if it's sufficiently subdominant, then this term can also be much smaller, and the CMB will be mostly dominated by the phi fluctuations. And this is kind of the basic reason why you would expect just completely different map in gravitational wave. Okay. So, so in this setup, we can try to find, we can calculate what is the energy density in the gravitational waves. Of course, it depends on the details of what exactly the phase transition is. But what is important for us is the omega gravitational wave actually goes as the square of the fraction of the energy density in the PT sector. Not linear, but actually square. And why, kind of a quick reason for that is in a phase transition, the strain of the gravitational wave should be proportional to the energy density being released, in the phase transition. And the energy density should be square of the strain. So you would expect something like energy density in the PT sector squared, which translates to this fraction when you calculate omega GW. And why that is bad is because if you're thinking about highly anisotropic gravitational wave, if you want to see a large delta chi, then you necessarily need to have FPT to be small, otherwise you mess up CMB. And it kind of quadratically reduces your isotropic gravitational wave signal, right? So seeing highly anisotropic gravitational waves in conflict with just even seeing the beginning, the isotropic part of the gravitational wave. So the question that we asked is this trade-off inevitable, or can you engineer models where you at least relax some of this trade-off? And one thing to observe is that from the CMB perspective, you need this sector that is undergoing phase transition to be subdominant at the time of CMB, right? But this fraction doesn't have to be constant. Like this sector can do whatever it wants in the beginning. It can be dominant in the beginning, but by the time of CMB, it should be subdominant, right? So then this is kind of the answer to the question. And adding to that the idea that matter and radiation does not dilute in the same way, you can easily construct a cosmology where you can get rid of some of the suppression in the isotropic background. So let me kind of unpack this image. So what we want to do is we want the phase transitioning sector to be dominant at the time of phase transition, so you do not have to pay the cost of FPT squared that we saw earlier. But then you want it to be subdominant at CMB so that you don't mess up observations from CMB. So basically what you use is that when the chi field gets to the bottom of its potential, it will undergo a phase of matter-like behavior, right? And matter dilutes slower than radiation, so there's a possibility that it overtakes the radiation that's coming from the inflaton reheating, right? And then when it reheats the phase transitioning sector, it will actually remain dominant over the radiation that's coming from phi. And let's say the phase transition occurs in that region. And at some late time, let's say there is some particle in the reheated sector from phi, or the non-PT sector, that again enters matter-like behavior, and it takes over the chi sector again. So there's a kind of twice overtaking happening. We have two kind of periods of early matter dominance to achieve this. And then you have the usual story. So in this, you kind of don't have to pay the cost of FPT squared at production, and by the time of CMB, you are perfectly safe. Of course, I said it too quickly. Yes, there is no suppression at production, but there is an additional dilution to gravitational waves because there's a period of matter dominance after gravitational wave production. But it turns out that this dilution is just one power of this fraction that you need at the end, the fraction in the PT sector at the end. So instead of paying the kind of quadratic cost, you only pay one power of FPT cost. Okay, so just to give you some quantitative idea of how this helps. So in this plot, I have just the gravitational wave spectrum, frequency spectrum, and let me explain what different lines are. So the solid lines, so dashed lines are for the simple model where you don't have any periods of early matter dominance. And the solid lines are with the model where you have PT, kind of phase transition happening when the sector is dominant using EMD. And I've chosen different amounts of anisotropy in the gravitational waves. And accordingly, I've chosen the fraction of energy density in the PT sector such that you kind of saturate the CMB constraints, right? So of course, as you increase the anisotropy, you need a smaller fraction. But one thing to notice is that in the simple model, before doing anything, if you follow these lines, you quickly start dropping. The isotropic component starts dropping because, of course, it has a FPT squared suppression. But in the new case, you only pay one cost, so you have a drop, but it's not as severe. So you can gain a couple of orders of magnitude in your signal, and something that was not observable in LISA could be observable now in this model. But of course, this is not the only thing. I should also show you what happens to the anisotropy. So on the left, I have basically in blue and green, I'm showing noise power spectra of various experiments, which is basically their sensitivity to different multipoles based on the design and the trajectory and the noise levels in these experiments. Again, the dashed lines are these various benchmarks in the old model where you, of course, expect drop in just the amount of signal. But with the new model, it so happens that all of these points actually get elevated to this dark line here. It is generally difficult to detect anisotropies, but there's a possibility that you see these highly anisotropic gravitational waves at least to a few multipoles with LISA. So there's some chance that LISA can potentially see some interesting anisotropies on top of isotropic signal with this model, which was just kind of impossible with the previous model. Okay, maybe let's just take a jump. Okay, I think I have time to talk about the second part as well. Okay, so I told you that what we needed to see these highly anisotropic gravitational waves was we needed some part where whatever is producing gravitational waves should be dominant and then become subdominant. And also the source of gravitational waves was phase transition. So you needed this additional ingredient on top of whatever else you have. So you also needed phase transition to happen. So we try to think, okay, can we kind of relax this and make kind of more natural model where you don't need so many ingredients? And so one interesting possibility from kind of modifying post-inflationary cosmology is that what if you have the chi behave in such a way that it has a matter-like phase such that it can take over the radiation coming from the inserton, but then it has a kination phase where the energy density dilutes much faster than radiation, so that it can just dilute away much faster and naturally become subdominant to the standard model plasma at the time of CMB, right? So then you don't need these two periods of AMD, just kind of one dynamics does it all. And secondly, what if the chi has like kind of more scale invariant power spectrum such that the modes that are re-entering during this period, they can actually just give you gravitational waves through induced or secondary gravitational wave mechanism. So that is what we try to do, and it's an ongoing work. So let me just tell you how to first get this part. So this actually occurs very naturally in these models called the classically rotating axion. This was first developed by Koushik and Raymond to solve various problems, but it has a very nice feature that does exactly what I told you it should do. Like, it has a matter-like phase and kinesion-like phase. And roughly what it looks like is during inflation, this field, radial mode, is kind of stuck at a very large field value, and it develops like scale invariant fluctuations. After inflation, it starts rolling, but when it rolls, there is a small explicit symmetry breaking along the axial direction, so it gets a kick. It doesn't just roll along the radial direction, it gets a kick, and does this kind of circular motion, such that when it's kind of in this phase, it dilutes mostly like matter, but at the end, when it settles into a minimum, it's kinetic energy dominated. And in this part, it acts like kinesion and dilutes like kinesion. This is a very nice model that kind of naturally accomplishes what we wanted. And so the idea is that because of this chi field, you have this period of early matter dominance and a period of kination. And so the chi will also have a scale invariant spectrum with fluctuations that are much larger than 10 to the minus 5. Now, the modes that are re-entering when this field is dominating, those will copiously produce secondary gravitational waves because the curvature perturbation is basically enhanced during this time. And because they're produced, when they're produced, even curvature perturbation on large scale is also enhanced because chi is dominating. The large scale anisotropy that they have is also inherited from chi. So basically now you have one scale invariant spectrum from chi with large amplitude. One part of it is giving you, the high k part is giving you secondary gravitational waves, and a low k part is giving you anisotropies on large scales. So one spectrum does both your jobs, so you don't need any phase transition or any other source of gravitational waves. So maybe quickly show you some results. So here again, I have some benchmarks where I'm just showing frequency spectrum of gravitation with what you'd expect. Now these are the benchmarks where this is the maximum allowed amplitude you can have in the chi field, the fluctuations can have in the chi field before the primordial black holes or some other constraint takes over. And maybe the takeaway, so the two different curves are for how long the domination lasts, so how long the chi sector dominates. So it's like a short dominance and long dominance. Strangely, the long dominant, if the chi is dominating for a long time, you have more severe constraints from primordial black hole formation. It actually, yes. So it's produced because at this time, the dominant perturbation is coming from chi, which is much larger. Yeah, curvature. Yeah, and then yeah, yeah. Yeah, so the modes, the modes that are re-entering during this time, so those modes are giving you secondary gravity. Yes, yes. So that's like the poltergeist mechanism. But here, so that in that mechanism, you start with very small perturbation, like at 10 to the minus 5. And because it goes as fourth power of perturbation, you need some mechanism to like bump it. But here, I'm saying that the chi perturbation is itself large. Like the chi perturbation can be 10 to the minus 2, 10 to the minus 3. So then you don't need any special mechanism. It can be a slow transition and you'll still get this. Yeah, thank you. Yeah, so one interesting thing is that the primordial black hole constraints become kind of important. So a larger period of dominance actually gives you a constraint that your perturbations should be small. So the signal actually becomes smaller. But I guess the takeaway is that you can get really large signals from induced gravitational wave backgrounds in this model, which are also highly anisotropic. Right? So you'll expect anisotropy also at this level, 10 to the minus 2, 10 to the minus 3, etc. Maybe the last thing is, yeah, you can also just kind of invert the problem where you can say, okay, when this domination happens, it's the temperature when the kination goes to radiation. And here on the y-axis, I have the strength of the perturbation in the chi sector. And basically, with various experiments, you can kind of see what kind of parameter space of this model you can probe. So the gray regions are already excluded by PBH and other observations. But with like future gravitational wave experiments, you can basically carve out these spaces for different values of dominance. So it's a very good opportunity for future experiments. Okay, and so good. That's the end. Here's the summary. So I hope I've convinced you that there can be new cosmological fluctuation maps, which are significantly different from CMB. And such maps can be realized in gravitational wave backgrounds, either with various sources, if from first order phase transition or induced gravitational waves. Gravitational waves with large fluctuations are interesting both experimentally, theoretically, and they'll just open up a completely new window into inflationary physics. And modified post-inflationary cosmologies would play an important role in just the prospect for even seeing these gravitational waves by enhancing their isotropic component. All right, that's it. Thank you so much for listening.
So thanks, Arushi, for the nice talk. Time for questions.
So what's the fate of inflaton in your second model?
So the inflaton is already reheated kind of standard model dark matter. So it just stays as the radiation.
If it's radiation, it can take over kinesin sooner or later. No, you have to fine tune the reheating of inflaton carefully.
Oh yeah, actually you do want it to take over. Like you do want the chi sector to dilute away quickly because this phi is the one that has the 10 to the minus 5 fluctuation that we observe in CMB, and the chi sector has larger fluctuations. So it actually should dilute away and become subdominant to this radiation.
So it's a highly weakly coupled.
Oh yeah, exactly. Yeah, true. Yeah, these two sectors must be weakly coupled. Again, if you thermalize, then you have nothing. You're different. Yeah, so typically in here, you need the field to be initially misaligned to a large field value, and you need some kind of some small explicit breaking, which is important when the field has large field value because it will be high dimensional operator, right? And so in the beginning, the symmetry breaking is actually relevant, and as the field starts rolling, the effect of symmetry breaking actually decreases. And so you initially have some kind of gradient in the axial direction, but then it goes away. Yeah, exactly. Yeah. So sorry, yeah, maybe I went over it too quickly. Yeah, so this phase is when it's kind of mostly the most of the energy is kind of in the potential, so it's rolling down along the quadratic potential, so it has a matter-like behavior. But at the bottom, because of this kick, it will have some rotational energy left at the end, and this is when the potential energy is small, but there's a lot of kinetic energy in the rotation, and that typically dilutes like kination. And Actually, quickly, why that is so? Because it's like, yeah, and it's the. No, I mean, even if it's just going along a quadratic potential, it dilutes like matter. Doesn't have to. Yeah, and also it is actually, in a way, it is oscillating, but it's also doing this. So if you just kind of take a cross section, I think it will also be doing this, but in this way also. No, actually, sorry, maybe I said it wrong. Sorry, it's not doing that. It's not doing that. But when it's going down like this, you can show that it dilutes. It has a to the minus 3 dilution.
Yeah, did you compute the the higher order correlators, the non-Gaussian correlators of delta GW?
Yeah, I didn't, but yeah, you're right. Like this model does have like the chi, just a misaligned chi field does have non-Gaussianity. So the gravitational wave should have non-Gaussianity. I mean, we haven't considered that, but yeah, it will definitely have non-Gaussianity. You're right. Are you asking it from the perspective of P-Base formation or induced gravitational wave?
No, in general.
Oh, in general. Okay.
Yeah, we can discuss.
Yeah.
Thanks for this nice talk. So in the first model, your inflaton and the axion-like particle, that is also weakly coupled, right?
Yes.
So there is, I mean, even at the level of potential or the field space, there is nothing.
Yeah, they must be weakly coupled. Yeah. Otherwise, you would not be able to keep the.
But there is a mass hierarchy between the axion and the inflatons, because the reason I'm asking, when the inflaton will go to its minima and oscillate, if its mass is, I mean, if it's heavier, then it will destabilize the axion maybe.
Interesting.
Because the axion is light and
yeah,
I mean they are in the same effective field theory. I mean they are.
I'll have to think about it. A priori, I think not much mass hierarchy. I would expect the chi field to be lighter because I want it to behave like matter after insulation ends. But I'm not sure. I'm not 100% sure. Maybe I can. Yeah.
Thank you.
Okay, thank you. So our next speaker is Oyon Chakraborty.